First of all, because everybody knows is scientific production, but in the second place, because over the years, is not only a close personal friend, but is being a friend of this institution, is being collaborating with us many times for many years, and we will continue. Now we are going to listen to why the scientific revolutions begin. Please.
Yes, well, in fact, I've learned a lot from this institution, I should say. And I've also enjoyed this particular workshop very much. Okay then, well, I should perhaps explain that I'm basically a person who's very sympathetic to Kuhn. But though very sympathetic to Kuhn, I don't agree with every single word he wrote, obviously. And the problem I want to discuss is one that suggested itself to me because I used to lecture on Kuhn once. And whenever I was lecturing on Kuhn, there were a number of points in his system which I felt sorry. I'm sorry, I speak rather loud enough. Is that all right? There were a number of points that I found a bit doubtful, and I want to deal with one of these today. So I'll begin by my introduction, which will say what the problem is. Now, according to Kuhn's model, in most branches of science, for most of the time, the research scientists all accept the dominant paradigm of the field and carry out normal science within the framework of that paradigm. Occasionally, however, a few of these research scientists challenge the dominant paradigm and try to develop a new one. If they are successful, we have a scientific revolution. The question I want to raise in this paper is why, in the midst of the usual normal science, do these occasional challenges to the dominant paradigm arise? Kuhn himself suggests an answer to this question. So in the next section, I will state and criticize this proposed solution to the problem. So if you accept Kuhn's general model, the problem is, why do scientists ever stop doing normal science and occasionally initiate a revolution? So I want now to go on to what Kuhn himself said on this. Now, what Kuhn writes is as follows. Normal science repeatedly goes astray, and when it does, then that is, the profession can no longer evade anomalies that subvert the existing tradition of scientific practice, then begin the extraordinary episodes known in this essay as scientific revolutions. I will characterize this idea of Kuhn's as the build-up of anomalies view. If an increasing number of anomalies occur in the dominant paradigm, this will lead to the paradigm being questioned and a departure from normal science. This view, which has a slightly Popperian flavour, actually it's falsifications which generate the revolution, seems very plausible and in accordance with common sense. However, I will now try to show that it does not agree well with historical facts. There may be periods when the dominant paradigm is beset with many anomalies, and yet science continues, normal science continues unchallenged. Conversely, scientific revolutions can sometimes begin when there are only a few and rather minor anomalies in the dominant paradigm. In order to argue for these claims, I will consider one of the classic examples of normal science, namely research in astronomy and mechanics from the time of the general acceptance of Newton's theory, maybe about 1720, to the beginning of the Einsteinian revolution, i.e. 1905. In fact, there were in the Newtonian normal science of this period a succession of anomalies, which often remained unresolved for quite long periods of time. In 1746, for example, and by the way, I take these examples from my PhD supervisor, Lacroche, who discusses them, Clairaut found that the progress of the Groome's apogee is twice what it should be according to Newton's theory. It turned out that Clairaut had exaggerated the size of this anomaly owing to a mathematical mistake, but there still remained the small anomaly of a secular acceleration. This was only successfully resolved within Newtonian theory by Laplace in 1787. So you had an anomaly for 41 years. The next anomaly to come to light concerned the planet Uranus, which was discovered in 1781. The first to compute its orbit was Maxwell, and he noticed that it had irregularities. In 1821, Bouvard made predictions using Newtonian theory of the future positions of Uranus, but subsequently observations revealed substantial deviations from Bouvard's theoretical values. So there were, from 1781 to for the next 50 years, or no, 60 years, there were really quite big anomalies about the orbit of Uranus. However, as we know, in 1846, this anomaly was triumphantly resolved by Heuristic and Leverrier. They explained the irregularities in the orbit of Uranus by postulating a hitherto unknown planet, and then using Newtonian theory to calculate where that planet should be. The new planet, Neptune, was duly observed on 23rd September 1846, only 52 minutes away from the predicted position. Leverrier, having resolved one anomaly in Newtonian normal science, went on to discover another. In 1859, he showed that the rate of precession of the perihelion of Mercury differed from that predicted by Newtonian theory by 38 seconds per century. Later, his estimate of 38 seconds was changed to 43 seconds. Leverrier tried to explain this anomaly in the same way that he had dealt with irregularities in the orbit of Uranus. He postulated a hitherto unknown planet nearer the Sun than Mercury. This hypothetical planet was even given the name Vulcan, but no such planet was ever discovered. In fact, the anomaly of the rate of precession of the perihelion of Mercury was never resolved within the Newtonian paradigm. However, as the anomaly was a tiny one, and similar anomalies had been successfully resolved on earlier occasions, it is unlikely that this anomaly reduced confidence in the Newtonian paradigm to any significant extent. Our analysis of this example shows that anomalies can frequently arise in normal science, and can in some cases remain unresolved for long periods without giving rise to a scientific revolution, or even significantly reducing confidence in the dominant paradigm. However, it is still possible that just before the scientific revolution, there is a build-up of a large number of anomalies, and it is this build-up which triggers the revolution. Let us next examine this hypothesis as applied to the Einsteinian revolution. When the Einsteinian revolution began, in 1905, I might say, it is beginning very exactly, the dominant paradigm was no longer just Newtonian theory, but a combination of Newtonian theory with Maxwell's electrodynamics. The two theories seemed to fit well together. Maxwellian theory postulated the existence of an ether and regarded electromagnetic radiation as waves in this ether. Now, the ether could provide a basis for the absolute space which Newton had postulated. In the Einsteinian revolution, however, this paradigm was replaced by one in which the existence of both the ether and absolute space were denied, and in which Newtonian mechanics and gravitational theory were replaced by the special and general theories of relativity. On the build-up of anomalous theory, we would expect that around 1900 there would be a large number of anomalies in the Newton-Maxwell paradigm. Was this in fact the case? As far as Newtonian theory is concerned, the only anomaly was that concerned with the perihelion of Mercury, which had been known since 1859, and which no one considered to be very serious. What about electromagnetic theory, the ether? To the famous quotation from Kelvin. By the way, it was Lakatos who drew my attention to this quotation, so I owe this to my PhD supervisor. Now, Lord Kelvin gave an address in which he considered ether theory in 1900. He remarked, quote, "The only cloud in the clear sky of the theory was the null result, is the null result of the Michelson-Morley experiment. So Lord Kelvin, one of the leading physicists of the time, only recognized one anomaly in the Maxwellian paradigm. However, it could be claimed that Lord Kelvin was wrong to consider this to be an anomaly, because it had been successfully explained in terms of the dominant paradigm. In his 1892 and 1895, Lorentz had explained the null result of the Michelson-Morley experiment of 1887. No, Michelson-Morley was 1887, using the contraction hypothesis. As this hypothesis had been put forward independently by Fitzgerald, it became known as the Lorentz-Fitzgerald contraction, or LFC. Now, for many years, LFC was dismissed as a purely ad hoc hypothesis, which did not satisfactorily explain the result of the Michelson-Morley experiment. This point of view is to be found in Popper in his 1934 Logical Scientific Discovery. However, Grunbaum introduced a new point of view in 1959, when he argued that the Lorentz-Fitzgerald contraction was not, in fact, an ad hoc hypothesis. Believe it or not, Popper actually accepted Grunbaum's criticism and said he'd made a mistake. He was always reluctant to do this, but on this occasion he said yes, it is an ad hoc, after all. And also Lakatos, of course, also accepted that the Lorentz-Fitzgerald contraction was not an ad hoc hypothesis. However, Holston, in 1969, continued to maintain that the Lorentz-Fitzgerald contraction was an ad hoc hypothesis, though he used ad hoc in a different sense from Popper. Holston's view was in turn criticized very convincingly by Zahar in his book on Einstein's evolution. Zahar showed that the Lorentz-Fitzgerald contraction was actually deduced by Lorentz from another deeper hypothesis, his molecular forces hypothesis, which Lorentz had introduced for reasons which had nothing to do with the Michelson-Morley experiment. Zahar concluded from this that the Lorentz-Fitzgerald contraction was not ad hoc in Holston's sense, nor does it seem Lakatos, as you probably know, had four different senses of ad hoc. It wasn't ad hoc in any of those, it wasn't ad hoc in Holston's sense. In fact, we can only conclude that the Lorentz-Fitzgerald contraction was not ad hoc. But if it was not ad hoc, it provided a satisfactory resolution of the anomaly created by the null result of the Michelson-Morley experiment. It follows that in 1900, there was only one anomaly in the dominant Newton-Maxwell paradigm, namely the tiny anomaly of the rate of precession of the perihelion of Mercury, an anomaly which had been known since 1859. So, if you're going to base the introduction of relativity on anomalies, you've only really got one, which was already 46 years old. In effect, there was no build-up of anomalies in 1900, only 5 years before the beginning of the Einsteinian revolution. Okay, well, of course, this is only one historical example, and unfortunately yesterday I got a bit nervous because historical case studies were apparently considered by some people to be anecdotal evidence. So anyway, so I should at least give several others, but I don't have time, so now he's not. But I'm just indicating that this is in a way something for further research, but I haven't been able to discover a scientific revolution which was preceded by a really big build-up of knowledge from my own not very extensive researches, so that's a question. Okay then, well, if we don't think that that's the reason why revolutions begin, we have to find another approach. And in the paper I want to suggest another approach. And the basic idea of this is that I think we have to go outside science itself and look at things outside applied science, namely technology and practical problems. So I'm going to use the abbreviation TECH, not just to mean technology, but technology and practical problems. So what I'm thinking about this, it seemed to me that there are two different ways in which tech, in a sense, can give rise to a scientific revolution. Advances in technology can precede a scientific revolution. Usually the relevant effect of the new technology is to enable better instruments for scientists to construct. This enables new observations and experiments to be carried out, resulting in a number of significant discoveries which involve new objects and processes. These discoveries are what give rise to the scientific revolution. I call this matter tech first, because the advances come before the scientific revolution and act as its efficient force. By contrast, there is also a tech last matter, which takes the following form. At a certain stage of development, there may be some urgent practical problems which cannot be easily solved within the existing scientific paradigm. Some scientists may be stimulated by the situation to try to solve these problems by changing the paradigm. This explains the beginning of the scientific revolution. If the new paradigm does indeed produce solutions to the urgent practical problems, then the scientific revolution will be successful. I call this pattern tech last, because the advances in tech occur after the scientific revolution has begun and as a consequence of the scientific revolution. Tech is here the final cause rather than the efficient cause of the revolution. In the next section, section 3, I will describe the tech first pattern in more detail and use it to explain the beginning of the chemical revolution. In section 4, I will treat the tech last pattern in a similar fashion, using as an example a revolution in medicine. So I now move on to my next thesis here, already given one, which is the chemical revolution. How do we explain the beginning of the chemical revolution? Now, in the tech first pattern, technological developments lead to new instruments, and with the help of these, a number of striking new discoveries are made. These then stimulate the beginning of the scientific revolution. It might be said then that in such cases, I'm replacing a build-up of anomalous theory with a build-up of new discoveries theory. This is quite correct, and it is therefore important to explain how anomalies differ from new discoveries in relation to the dominant paradigm in the branch of science in question. So I'm, in this pattern, looking in terms of new discoveries rather than anomalies. So what's the difference between the two? As we saw from our analysis of Newtonian normal science in the period from about 1720 to about 1905, anomalies are concerned with objects which are standardly dealt with in the paradigm. In the examples we considered these were the moon, planets, such as Uranus and Mercury, and in the Michelson-Morley experiment, the ether, which was a basic object in the extended Newton-Maxwell version of the paradigm. Characteristically, anomaly arises because the paradigm predicts some result regarding the object which is contradicted by observation, so that some adjustment is necessary. In the case of new discoveries, however, the objects may be quite new and may never be considered to reveal the paradigm. Moreover, these new objects may behave in new and unfamiliar ways. How such new objects can be handled within the dominant paradigm thus becomes a much more problematic matter. The old paradigm, after all, was developed in complete ignorance of the new objects and phenomena. This is bound to suggest to some researchers, the revolutionaries, that a new paradigm is needed to deal with the new entities. Of course, not all researchers will reason this way. Other researchers, conservatives, will try to explain the new discoveries in terms of the old paradigm. In this way, a build-up of new discoveries creates the conditions for the beginning of a scientific revolution. I will now try to illustrate this in the case of the chemical revolution. Okay, so I'll now give my example of the chemical revolution, which has recently been dealt with by Professor Chang. So I'm hoping to discuss this with you with some, perhaps revise my account a bit. But anyway, I'll give you my present account of this revolution. As you know, it was the revolution replaced the phlogiston theory by the oxygen theory. Now, the phlogiston theory was designed to explain two processes which were regarded as essentially the same, namely combustion and calcination. An example of combustion would be the burning of charcoal. Calcination consisted of the conversion of a metal to its calx, for example, the conversion of iron to rust. These processes were explained by postulating that charcoal and metals were a rich and inflammable substance, phlogiston, which was expelled in the process of combustion or calcination. From the start, there was a problem about weight change in the phlogiston theory. When charcoal was burnt, there remained ashes which weighed less than the charcoal. This was consistent with the assumption that the substance, phlogiston, had been expelled. However, when a metal was converted to its calx, the calx weighed more than the original metal. Supporters of the phlogiston theory explained away this anomaly in various ways. For example, Boyle and Boerhaave explained it by supposing that in calcination, fire particles enter the calx and account for its increase in weight. There were other explanations, but that was unpopular. The phlogiston theory could also explain the reverse of calcination, that is, the conversion of calx into metal. For example, if we heat the calx with charcoal, since charcoal is very rich in phlogiston, the phlogiston from the charcoal combines with the calx to give the metal. Okay, so the phlogiston theory was quite successful in explaining these phenomena of combustion and calcination. Now, what gave rise, so I played into the chemical revolution, was, which resulted in the overthrow of the phlogiston theory, was a build-up of new discoveries which were not in the field of combustion and calcination. That was the field where the old paradigm had been developed. These new discoveries were new gases whose chemical and physical properties were investigated. Although the word gas had been invented by Van Helmont in the 17th century, it was not much used by chemists in the 18th century. What we now call a gas was then referred to as an air or elastic fluid. The discoveries concerning new airs were in turn made possible by technological innovations in the devices used by chemists. Perhaps the most important of these was the invention of the pneumatic trough for collecting gases over water. This is a beautiful picture of the 18th century technology. Hale's pneumatic trough. Stephen Hales was a clergyman. What happened in those days, if you followed an academic career in Britain, you got your fellowship at Oxbridge, well, if you're lucky. But then, if you remained a bachelor, you were okay. But if you married, you were not allowed to hold your fellowship anymore. So what they did was they gave you a living in that state, some place in the country where you became the vicar of the church. And a lot of these vicars, I don't know how religious they really were, but they seemed to have spent their time doing mathematics and science and so on. So Stephen Hales was one of this crowd, and what he really liked doing was, as I say, collecting new airs. He invented this device for doing so. He took lots of different things, just sort of heated them up. It was very Baconian, and he would collect the gas they gave off. So he became very enthusiastic and published a book called Vegetable Statics in 1757. Now, Hale's pneumatic trough was developed by later scientists. Figure 2 shows the form of the pneumatic trough, which is a bit more sophisticated, used Priestley for producing the gas which we now call oxygen. As you know, he didn't call it that, he called it dephlogisticated air. Now, both Cavendish and Priestley also modified the pneumatic trough for water-soluble gases by collecting the gas over mercury rather than water. Of course, the pneumatic trough was only one of the pieces of apparatus which the chemists at the time used for their investigations. Figure 3 shows the burning glass, which Priestley used for heating counts of mercury. So he heated counts of mercury to produce oxygen, dephlogisticated air. And also improved analysis of water. Now, the next important advance out of Hales was published by Joseph Black in 1756. He obtained a gas by heating lime, leaving a residue of quicklime. This new gas Black called fixed air, is what we now call carbon dioxide. However, Black also obtained the reverse reaction. If quicklime is dissolved in water to get lime water, and then fixed air is bubbled through lime water, lime appears immediately as a milky precipitate. This suggests that the air has become fixed into the lime, hence the name fixed air. The startling nature of this discovery is emphasized by Black's colleague John Robinson, who wrote in his introduction to the printed version of Black's lectures on chemistry, published posthumously in 1803, he, that's Black, had discovered that a cubic inch of marble contained about half of its weight of pure lime, and as much air as could fill a vessel holding 6 gallons. What could be more singular than to find so subtile a substance as air existing in the form of a hard stone, and its presence accompanied by such a change in the properties of the stone? So this is really quite a very dramatic discovery, which was made by means of these new apparatus. Black also studied many of the properties of this fixed air. He knew that it extinguished flames, and that mice put in an atmosphere of fixed air died. It wasn't very good for animal rights, this period, because as soon as any of them discovered a new air, they would immediately put mice in them to see what happened. Usually the mice died, but actually when they discovered dephlogisticated air, the mice became more lively and started jumping around in an instinctive fashion. This immediately gave Priestley some ideas for commercial applications, namely produce oxygen and get people to inhale it, and they would become, it would make them feel good. So he actually started a little business on that, but anyway, that's just by the way. He found, to continue with Black, that the density of fixed air was greater than that of common air, and tests with alkaline substances showed that it behaved like weak acid. An unknown air could be identified as fixed air by these properties, and by the fact that it immediately created a milky precipitate when bubbled through lime water. So you had a very simple test for recognizing that something was fixed air. Using these tests, Black was able to discover a number of different ways of producing fixed air. He found that fixed air was expired in respiration and produced in alcoholic fermentation. He found that fixed air could be produced by burning charcoal. That's going to be very important. You burn charcoal, you got fixed air, or dissolving some mild alkalis in acid. Black's pioneering work on fixed air was followed in the next 20 years by a series of discoveries of other new gases and the study of their properties. In 1766, Cavendish published a study of what he called inflammable air, as our Persian. In 1772, Rutherford, a student of Black, removed from common air all that could be eliminated by respiration and common combustion. He recognized that what remained was a new air which he called lymphatic air. This is our nitrogen. In 1772, Priestley discovered nitrous air and some other airs. The most interesting such error was one he obtained in August 1774 when he used his new burning lens. Yeah, he used his new burning lens to extract an air from the curious calcinatus per se, our mercury constant. Priestley had to interrupt his work on this new air, which is our oxygen, of course, to accompany his patron Lord Sheldon. In those days, you got your finances by having an aristocratic patron who was interested in science, you see. But there were some snags, you had to accompany your patron on his European tour. But this actually was quite useful because Priestley met Lavoisier in Paris in October 1774 and was able to tell him about the new air, which Lavoisier immediately proceeded to investigate. Though he drew rather different conclusions from his experiments. Priestley did. My thesis then is that this build-up of discoveries concerning new gases and their properties gave rise to the chemical revolution. This thesis is supported by a most interesting document written by Lavoisier, probably on 20th February 1773. In this document, I say probably because it's actually dated, it's a rather curious one, it's actually dated 1772, but it's in a notebook dated 1773. So there's a very interesting scholarly controversy, which I won't bore you with, and I think most scholars think 1773 is the correct date. But we're all scholars, I must mention this one. Now, Lavoisier says that the aim of his program, he writes down, you see what is beautiful about Lavoisier is he writes down exactly what his research program is. He writes down, this is what I'm going to do. And this is he describes it. He says that the aim of his program is that of making a long series of experiments on the elastic fluid that is set free from substances, either by fermentation or distillation, or in every kind of chemical change, and also on the air absorbed in the combustion of a great many substances. He mentions similar experiments by predecessors, but regards them as inadequate. This is a quotation from this document. However numerous may be the experiments of Messrs. Hales, Black, McBride, that's McBride, Jacquin, Krantz, Priestley, that's Priestley, and De Smith, in this direction, nevertheless, they come far short of the number necessary for a complete body of doctrine. I've been bound to look upon all that has been done before me as merely suggestive. Interesting heuristics there. It's suggestive. I have proposed to repeat it all with new safeguards in order to link our knowledge of the air that goes into combination or that is liberated from substances with other acquired knowledge and to form a theory. And he actually then makes his remarkable prediction that this research program will lead to a scientific revolution. I think this is the only case I know of where a scientist says, I'm going to carry out a scientific revolution, and he does so. He says, the importance of the end in view prompted me to undertake all this work, which seemed to me destined to bring about a revolution in physics and chemistry. Well, I don't know about physics, but in chemistry it did. So he was right. Now, the important point I'd like to stress here is that he thinks that it is the study of the new gases and their properties which will give rise to this revolution. So this is in accordance with the view forward. Now, the impact of the discovery of the new gases and their properties was different for different researchers. Lavoisier decided quite early on, perhaps as early as November 1772, that the phlogiston theory would not explain the new results satisfactorily, and that the development of a new theory was needed. Because he does mention a new theory there that he wants to develop. The leading English chemists, Cavendish and Priestley, on the other hand, tried to fit the new results into the framework of the old phlogiston theory. So this is the model that I'm trying to describe. You've got a whole series of new phenomena, which the phlogiston theory was never designed to explain. So how do you explain these new phenomena? The conservatives say, fine, you develop the phlogiston theory and explain all these new phenomena. So, the revolutionary scientist, in this instance, Capozzi, says, no, it's never going to explain these new phenomena. Let's develop a new theory. So this is how we get a Kuhnian situation emerges. Okay. Now, against this account, it might be objected that issues to do with combustion and calcination still remain central. And that, for example, Lavoisier's key experiments of 1772 on the burning of sulfur and phosphorus, rather than results about new gases, were what convinced him of the falsity of the phlogiston theory. It is, of course, true that experiments on combustion and calcination remain central, but there was a close connection between these experiments and the new results concerning gases. Planck had shown that lime water could be converted into lime through the fixing of his new air. This result favoured the view that combustion and calcination might involve the fixing of air to produce an addition theory of combustion and calcination, as opposed to the subtraction theory of phlogiston. Phlogiston is the subtraction theory because combustion, you're taking something out in the phlogiston. The addition theory is where you add something, namely oxygen. And the fact that you can add fixed air to lime water and get lime is something that does suggest an addition theory. Earlier we remarked that the phlogiston theory explained the weight loss when charcoal was burned and turned to ashes. However, the weight gain when a metal was turned into a calx was an anomaly. With an addition theory, the situation is exactly reversed. The weight gain when a metal turned into a calx could easily be explained, because we're adding something. But the weight loss when charcoal was burned constituted an anomaly. However, as Lavoisier must have realized, some of Planck's results concerning fixed air showed a way in which this anomaly could be resolved. Planck had shown that fixed air is produced when charcoal is burned. Perhaps when account is taken of this fixed air, there will be a weight gain from a weight loss. This is, of course, the modern explanation of the situation. So the new results on gases not only suggested an addition theory, but also showed a way to resolve the anomaly in such a theory. So to sum up, technological developments in instrumentation, such as the invention of the pneumatic trough for collecting gases over water, and later mercury, enabled researchers to discover a series of new gases in the period from 1755 to 1770, and to find out the properties of these gases. These discoveries concerning new gases were the trigger of the chemical revolution. This is an example of what I call the tech first pattern. This is where we get technological innovations lead to discoveries, and that provokes the revolution. However, I think there is another pattern, what I call the tech last pattern, and so I will illustrate this with another case history. So this is the last section where I go on to consider what I call tech last. The tech last pattern is quite different from the tech first pattern. A tech last revolution is not preceded by developments in technology. They produce new instruments and a build-up of discoveries. What precedes the revolution is rather a major unsolved practical problem. Attempts to solve this problem within the current paradigm have failed, and this encourages some researchers to seek a solution to the problem by changing the paradigm. Note, however, that the failure to obtain a solution to the practical problem may not be an anomaly in the current paradigm, because there may be no guarantee that the problem is in fact soluble. For example, a lot of people have failed to discover perpetual motion machines, but this didn't show that conservation of energy was wrong. It just showed that the problem could not be solved. So this is not to say the fact that you can't solve a problem in a paradigm doesn't necessarily constitute an anomaly. On the other hand, it does give you a stimulus. It's the stimulus of hope. if we change the paradigm, we might be able to solve the problem and get a good solution. I will now illustrate these features of the tech glass mantle by an example drawn from the history of medicine. One of the biggest revolutions in medicine started about 1865 and had largely succeeded by about 1885. This revolution established the germ theory of disease as a new paradigm for medicine and brought antisepsis into the practice of surgery. Nowadays, we are all completely familiar with the idea that a wide range of diseases are caused by bacteria or viruses. In fact, if you've got something, the most likely explanation for a doctor will give you, oh, it's a virus. Even if there's no actually medical proof in most cases. But this is part of the dominant paradigm for a lot of diseases, of course. When I started studying history of medicine, I found it very surprising to learn that the germ theory of disease was, apart from a few precursors, only introduced around 1865. Extraordinarily late. It only came to be generally accepted by the medical profession around 1880. Before that, there was something, the dominant theory was something called the miasma theory, which incidentally did have a lot of successes. Well, I won't go into details of that, it's quite an interesting story. Now, the germ theory of disease was successfully used to explain two diseases: wound suppuration, sepsis, and anthrax. Anthrax is a disease of both humans and cattle. It got a bit of publicity. Do you remember immediately after 9/11, a lot of senators in the US were sent weapons-grade anthrax? I don't know why was this ever cleared up why that happened, but anyway, it's the same disease, but now, of course, in our enlightened modern times, it's used as a biological weapon. But at the time we're talking about, it was a disease of mainly cattle, sheep, but also humans as well. A French doctor called Casimir Delay, 1812 to 1882, suggested in 1863 that this disease was caused by microbes, which he called bacteria. His view was initially criticized and rejected. So he's a pioneer. There were indeed good objections to his account of anthrax, and it was rejected until there was further work done on the disease by Koch and Pasteur, and they actually developed his hypothesis in a way such that it came to be accepted. So that was one thing, one way into the germ theory. The other pioneer of the germ theory of disease was Joseph Lister. He used the germ theory to explain wound suppuration, and was more successful today as he managed to get his view accepted by the medical community. I will now analyze what led Lister to begin his revolution in medicine. Now, Joseph Lister, 1827 to 1912, was elected to a fellowship of the Royal Society in 1860 and appointed as Regius Professor of Surgery at Glasgow the same year. It was while at Glasgow that in 1865 he introduced his antiseptic system of surgery. By the way, I just mentioned one sad fact, which when I was studying this. Lister was actually English, though he had a job in Scotland. Now, this may seem to you a rather trivial point, but my grandmother was Scottish, believed that all the important advances of humanity were made by the Scots. She had a somewhat nationalistic view, and one of her examples was Lister, and for years I believed, because he made this discovery in Glasgow, if someone's in Glasgow, they must be Scots. But no, he was an English person, born in London, but he had got a job in Scotland. So, and I was amused when I went to the Pasteur Museum in Paris, that it said here, correspondance avec Joseph Lister, le chirurgien écossais. A mistake. I didn't point it out that he was actually Anglais. Anyway. To understand Lister's innovation, it is necessary to know something about surgery as it was practiced in the 1860s and 1870s. Anesthesia for surgery had been introduced in 1846. Really, that's one of the most important dates in medicine. That's another story. The horrors of pre-anesthetic surgery disappear in 1846. And actually Lister was at that time a medical student at University College London, and he actually attended the first operation to be carried out in Britain using anesthetics. Anesthetics were invented in Boston, in the US, and then I think immediately they were taken out to Britain and France and other places. So the horrors of pre-anesthetic surgery were over, but surgery was still in a very unsatisfactory state. The main problem was that after any operation, the wounds, instead of healing, might become severely inflamed and then turn septic, producing pus. Such sepsis or suppuration often had fatal results, but it was not known why it occurred. And I quote here from Harding Raines, who was himself a surgeon who took out history of medicine, and he gave the following vivid description of what could typically occur in hospital in the 1860s. Yes, this is what happened in 1860. So don't think life is all that good in the 19th century. People who want to go back to the 19th century, there were problems. Here's the quotation. And why was there such a danger? We today know the answer: infection by bacteria. But Lister and his world did not. They saw the effects, not knowing the cause. They had to stand and see the skin and flesh around the wounds become intensely red and hot and swollen. This suppuration, as they called it, would get worse. The skin turning blank would again be hot. Foul-smelling fluid and pus would run out of the patient due to the rottenness of putrefaction, which seemed to be eating its way into the body. The body would become full of poison, septicemia, causing shivering, high fever, wasting the whole body, which would end in death. The whole state of affairs they called sepsis. It was indeed dreadful sepsis. What was the effect of all this on patient mortality? Mr. Erickson, who was Professor of Clinical Surgery at University College London, published a booklet on the question, Hospitalism and the Causes of Death After Operations, in 1874. This is a kind of the beginnings of evidence-based medicine. As regards death after amputations, he regarded a mortality rate of 24 to 26% as a very satisfactory result. He managed to show that University College Hospital had been in top of the range. Only a quarter of patients who had their legs amputated died. And similar levels were achieved at the Pennsylvania Hospital and the Massachusetts General Hospital in Boston. However, the Edinburgh Infirmary was 43%, the Glasgow Infirmary was 39%, in Paris around 60%, that was the worst, and in Zurich 46%. In military field hospitals, the mortality rate for amputations was between 75 and 90%. In fact, in the Franco-Prussian War, which was carried out in 1870, that was the, if you were unlucky enough to have a cannon ball or something hit your leg, and you had to have it amputated, you had between 75 and 90% the chance of death. In Tolstoy's War and Peace, one of the characters does have their leg amputated and survives. I don't know this episode, but that would have been an unusual experience. I think it was a few years earlier, in 1871, Sir James Simpson, who had introduced chloroform as an anesthetic, published a series of articles on hospitalism, in which he made the famous claim: the man laid on the operating table in one of our surgical hospitals is exposed to more chances of death than the English soldier on the field of Waterloo. So what he worked out was how many of the English soldiers died at the Battle of Waterloo, and the percentage was less than those who died after having amputation. And in fact, it was between 30 and 40%. And this is to say nothing of things called hospital diseases. If you went to hospital at all, you were very likely to get something called a hospital disease, which is usually fatal. And some of these problems are coming back now, so they're not, we can't just dismiss them. And actually there was a proposal at this time to abolish hospitals altogether. So you can see it's not a very sensible system. Okay, now what were the medical profession thinking about this problem? Harding Raines is quite correct to say that the cause of sepsis or suppuration was not known in the early 1860s. Nevertheless, there were theories of sepsis at that time. Surgeons had to concern themselves a good deal with broken bones. Such fractures were divided into simple and compound. In a simple fracture, the skin remained intact. This is the difference, quite an important difference. If you have a simple fracture, the skin remains intact. The bone is broken or fractured, but the bone doesn't come out and penetrate the skin. Whereas compound fracture, broken bone does penetrate the skin. Now, the important point to note was that simple fractures could normally be set and then healed up without any problems. So if you had a simple fracture, basically there was no problem. It was set and it healed up. But if you had a compound fracture, it was a different matter. In general, suppuration set in and the leg had to be amputated. I was lecturing on this. I always used to ask the class, had any of you had a compound fracture? So if you were in the 19th century, there was one student, I remember, who broke her wrist. It was actually a compound fracture. So I think, well, you wouldn't have that arm now, even if you would survive at all. And it's quite interesting, this is quite interesting from the point of view of history, because one of the extraordinary things about the Middle Ages is that they had all these tournaments. But of course, you could easily break a bone in a tournament, and that was very often fatal, so they were really pretty dangerous things. And if you read Chaucer, for example, who was trained medically, he does describe all the symptoms of suppuration. One of his characters in The Knight's Tale gets a wound at a tournament, and he describes how it suppurates and then he dies. So this must be pretty common. Why they took up this procedure, I don't know, but anyway, that was a social custom at the time. Now, the point is that these facts suggest that exposure to air was one of the causes of sepsis. And this fitted very well with the miasma theory that diseases are caused by bad airs. So if you applied that to the chemistry of air, which was known at the time, the conclusion was reached that sepsis was brought about by oxidation. Now, so that was a standard theory. Suppuration occurs because air gets in, it carries out a process of oxidation, and that produces suppuration. We know Lister's own view in the early 1860s because he wrote some notes on suppuration on 12th December 1861. These have survived, and in them, Lister concludes that bodily fluids, after they have been acted on by air, acquire chemical properties which cause suppuration. So this is quite a reasonable theory given by the background at the time. This kind of approach was supported by the general background in science and medicine. In medicine, it was believed that many diseases were caused by miasmas or bad airs, while chemistry was one of the leading sciences of the time. All this suggested the suppuration of the chemical process initiated by exposure to air. The only problem with this theory was that it seemed to make it almost impossible to prevent suppuration, since in most operations air could not be excluded from the wounds. Lister's two teachers, whose names were Liston, confusingly, Liston and Syme, tried to devise ways of dressing wounds which would keep out air. Liston, he was in University College, he used water dressing, and Syme, who was in Edinburgh, used dry dressings. Lister tried both, but without much success. So the problem of sepsis appeared to be it occurred because air and oxygen got into the wound, and there seemed to be no method of excluding it. So what could you do? Well, then Lister had his eureka moment, which was caused by a conversation with a colleague at Glasgow. Thomas Anderson, probably he really was Scottish for all I know, who was professor of chemistry. In 1865, Anderson suggested to Lister that he should read some interesting recent papers by a French chemist, Louis Pasteur, who had been doing research into fermentation. Now, incidentally, there was a connection between Lister and fermentation because Lister's father was actually a wine merchant who was an amateur scientist who had invented a new type of microscope which was used by Pasteur. So there was also so interesting in the connection. Anyway, Pasteur had been investigating fermentation. So Lister read, again, interdisciplinarity, nothing to do with medicine and surgery. He read Pasteur's work on fermentation. And this gave him his key insight. Because up to 1856, fermentation had been thought to be a chemical process, a theory which went back to Lavoisier. However, in 1856, Pasteur, who was then professor of chemistry at Lille, did some research into the production of ethyl alcohol by fermenting beet sugar. Pasteur concluded that fermentation is not a chemical process, but is brought about by a microorganism, yeast. He published his results in 1857 in his Memoirs sur la fermentation appelée lactique. And this led in the next few years to the majority of the scientific community coming to accept the microbiological theory of fermentation. Another important result which Pasteur had shown before 1865 was that the air is full of microbes which float on dust particles. We can now reconstruct how the study of Pasteur's writings influenced Lister. Lister's work on wound sepsis had suggested that air was an important factor in causing suppuration, but he still thought that this must be due to chemical changes produced by air. On reading Pasteur, however, he rapidly reached the conclusion, this is the eureka moment, that it was not the air itself, but microorganisms contained in the air which were responsible for wound sepsis. This is how Lister himself puts it in his 1867. So this is an account of himself how he presents it. To prevent the occurrence of suppuration with all its attendant risks was an object manifestly desirable, but till lately apparently unattainable, since it seemed hopeless to attempt to exclude oxygen, which was universally regarded, London paradigm, as the agent by which putrefaction was effected. But when it had been shown by the researchers in Pasteur that the septic properties of the atmosphere depended not on the oxygen or any gaseous constituent, but on minute organisms suspended in it, which owed their energy to their vitality, it occurred to me that decomposition in the injured part might be avoided without excluding air, by applying as a dressing some material capable of destroying the life of the floating particles. Upon this principle, I have based a practice of which I will now attempt to give a short account. So Lister's aim was to find some way of keeping airborne microbes out of wounds. In principle, he could have done this by heating, filtration, or the use of chemical antiseptics. But in practice, he regarded the last option as the only feasible. For his antiseptic, Lister chose carbolic acid, which had been used as a disinfectant in dealing with sewage in Carlisle and was easily available. His first attempts at antiseptic surgery in March 1865 consisted of an operation on the wrist and a compound fracture. Unfortunately, both failed, but Lister then refined his techniques and he got his first big success on the 12th of August 1865
Well, I don't actually have a photograph, but this is a sort of romantic picture of what happened. This was, the patient was an 11-year-old boy called James Greenlees, who was brought to Glasgow Infirmary with a compound fracture of his leg, caused when he was run over by a car. By the way, traffic accidents were very common in the 19th century, although there were no cars. There were lots of cars. And people were always getting run over by cars. So it was again, it was more dangerous than right then. Anyway, the boy was anesthetized with chloroform, and the wound washed out thoroughly with a solution of carbolic acid in linseed oil. It was then dressed with a mixture of putty and carbolic acid, and the putty we used to hold the antiseptic in place. The dressing was extended some distance from the wound, covered with thin foil to prevent evaporation of the carbolic acid. Finally, the leg was fitted with bandages to hold the split and dressing in place. 4 days later, the dressing was removed. The skin was very sore, but was no sign of suppuration. Normally, suppuration would have begun by this time, so it was an encouraging sign. Lister repeated the dressing and waited 5 days. During this time, the boy's temperature remained normal, and he did not lose his appetite. When this dressing was removed, the skin around the wound had been burned by the carbolic acid. A final carbolic acid was applied and then for another 4 days. By this time, the wound had begun to heal, and Lister judged that the risk of suppuration had passed. He applied a water dressing to give the skin burnt by the acid a chance to heal as well. 6 weeks and 2 days after his accident, James Greenlees left the hospital with 2 whole legs, which for the time was extremely remarkable. So this was the rather, if you like, romantic story of how this submitted the scientific evolution. But the philosophical point I want to make is that here it's what I call take last, which means that there's a very urgent practical problem. It is impossible to solve it within the dominant paradigm. So this encourages some to think, well, supposing we change this paradigm, we might get a solution. Of course, it might not work, but that gives a motivation for not continuing with modern science, but trying a bit of revolutionary science. So that's the technique. Okay, that's all.